Hello again to my algebra class. We're moving on today. We'll be in lesson 61. This one mathematically is fairly easy, but it takes some thinking and some logic on working these problems, so you got to be careful. It is a lesson on subsets, and subsets are interesting because it's basically when you have numbers that may belong to more than one group. Sometimes all the parts of one group are also a member of another group, so we call it a subset of that, okay? It's kind of like, me personally, I fall into several classifications. I am a human, I am a male. You can also go further than that. You can say I am a father, I am a brother, I am a son. Not everybody is all of those things, but I happen to fall into all of those groups, okay? And some of them are subsets of other groups, like the fact that I said I am a male. Well, that is a subset of humans because all males are human, when we're talking about people anyway. On the other hand, the opposite is not true. All humans are not males, okay? Because we have other people besides just us men. So subsets, they can be a little tricky, but like I said, you got to use a little bit of logic here. And so we're going to look at example 1, and I'm going to explain what this means. In example 1, they give us 3 groups of numbers, 3 sets of numbers. They tell us what they are. The first one is set D. It only has 3 numbers in it. It has the numbers 0, 1, and 2. And then they tell us about set E. Now, E has actually an infinite number of numbers in it because, as you can see, it has the numbers 1, 2, 3, and then the ellipses at the end tell us that that list goes on forever. So it's actually 1, 2, 3, 4, 5, 6, 7, 8, going on up 100, 1,000, a million, a billion, going on forever. So this list just goes on forever. And then G is another limited group. It only has 3 numbers in it. It is 1, 3, and 5. So they specify for us these numbers are in set D, these numbers are in set E, and these numbers are in set G. And then they give us a list of 3 statements, and they want us to tell whether these statements are true or false. Now, this weird little symbol here, which kind of looks like a sideways U, this just means that this first thing is a member of this second thing, and we are saying whether or not this is true. So this first statement is saying E is a subset of G. And for that to be true, then all of the things in E have to also be in G. So let's see if that's true. Are all of the numbers in set E also in set G? Well, the 1 is, that's good, but the 2 is not. 2 is a member of set E, but it's not in set G. So E cannot be a subset of G. In fact, there's a whole lot of other numbers that are also not in set G because 4 is not in there, 6 isn't, 7, 8, 9, 10. Remember, this list goes on forever. So these numbers are not all in set G, so then it cannot be a subset of it. So we would say this one is false. All right, and then we would look at B here, and let's think about what this one's saying. This one is saying that G is a subset of E. So it's saying all the members of this set are also a member of this set. Well, is that true? Well, 1 is a member of this set, so that one's good. 3 is also a member of this set, so that one's good. And then 5 is also a member, even though it's not listed here. Remember, the ellipses tell us that this list continues, so it will get to 5. So that means 5 is also a member of this set. So this one is true. All the numbers in set G are also in set E. So this one is true. And this is kind of like the example I gave a minute ago. These are opposites of each other. One of them is false. One of them is true. It's like I said, every male is a human, but the opposite is not true. Every human is not a male. So in this case, everything in set E is not a member of set G, but everything in G is a member of set E. So it's tricky. You got to really think about each one. They give us one more here. They want us to look at if D is a subset of E. So let's look at list D here. It's pretty close except for one thing. 0 is actually not in this list. The 1 is in there, the 2 is in there, but unfortunately the 0 is not. So because of that, all 3 of these are not in this one, so this one is also false. All right, now those are very specific examples they give of individual numbers. In the second part of the lesson, they go a little bit more in-depth and they talk about actual different sets of numbers and how they're subsets of one another. So you can see it over on page 248 and 249, and it gives us a reminder about the different sets of numbers. You have natural numbers, which are the numbers we learn to count with. It's basically this set right here, 1, 2, 3, 4, so on. You want to count 0 of something, you want to count negative of something, you want to count half of something. You would count 1, 2, 3, 4, and so on. They then list the whole numbers, which are almost the same thing, except they start with 0. So 0, and then 1, 2, 3, 4, and forever. And then they list integers. Integers include negative numbers. Again, no fractions though. So the list of integers, as you can see in the book, it goes forever both directions. It counts negative numbers backwards to infinity. It counts positive numbers forward to infinity. And you got the 0 right smack dab in the middle. And then there's 2 others that we haven't really talked about too much. And every number is going to fall into one of these 2 categories. Every number is going to either be a rational number or an irrational number. So for the longest time, I had trouble with this until one day I read what rational means. Rational just means that it can be written as a ratio. That's why it's called rational. It doesn't have to do with whether it makes sense or not. It's just the fact that it can be written as a ratio. So remember, a ratio we write like a fraction. So if a number can be written as a fraction, it is a rational number. So there's all kinds of numbers that can be written as fractions. A whole number can be written as a fraction. So like the number 7, you could write it as 7 over 1. Therefore, it is a rational number. If you have, look at that, we're still in school, got the bells ringing. If you have a repeating decimal, for example, 0.3 with a repetend over it, like so 0.3, that 3 repeats forever, that is actually a rational number because that is a fraction. It is the fraction 1/3. And if it's written as a fraction, it is a rational number. Now, if it is not a repeating decimal, but it's one that does go on forever, then it is an irrational number because it cannot be written as a fraction. A good example of one of those is pi. A lot of times we abbreviate pi as 3.14, but we know that it actually continues going on forever. 3.14159265, blah, 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 blah. It continues going on forever and ever and ever, and it never repeats. In that case, that is an irrational number because there is absolutely no way to write that exactly as a fraction. So that's what you want to keep in mind. Rational numbers can be written as fractions. Irrational numbers cannot be written as fractions. Another good example, the square root of 2. That cannot be written as a fraction. If you put it into your calculator, it's going to go as far as it can with decimal numbers. It actually will continue on forever. It will not repeat, so that will be an irrational number. However, if we did like the square root of 4, well, the square root of 4 is 2, and 2 can be written as a fraction, 2 over 1. Therefore, that one is a rational number. So that's what you want to keep in mind. Rational, it can be written as a fraction. Irrational, it cannot be. Now, on page 249, they kind of show how all of these things relate to one another as far as sets. Everything we're dealing with is considered a real number. And then, like I just said, real numbers are divided into 2 groups. You've got irrational, and if it's irrational, it's not going to be anything else. And then you've got rational. And some rational numbers are integers, and some are whole numbers, and some are natural numbers or counting numbers. So sometimes these sets overlap, and you can see that in the diagram there on page 249. Okay, very quickly, on page 250, we'll look at a couple more examples, and then we'll be done with this. On example 2, 61.2, they ask us, 1/2 is a member, that's what that little symbol means, is a member of what subsets of real numbers? All right, well, it's not much, because remember, everything is a real number, so no matter what, it's always going to be in a set of real numbers, so that will always be 1. And then we said every real number is either rational or irrational. In this case, it can be written as a fraction, because it is a fraction. Therefore, it is rational. And then rational numbers can sometimes be natural numbers, whole numbers, or integers. This one is none of those, though. It's not a counting number, it's not a whole number, and it's not an integer. So it's only real or rational. All right, let's look at example 61.3. On this one, they ask 5 is a member of what set of real numbers? Well, of course, it is a real number. We can list that one always. And then remember, every number is either going to be rational or irrational. The number 5 can easily be written as a fraction, 5/1. Therefore, it is rational. And rational numbers can be, they don't have to be, but they can be counting, natural numbers, whole numbers, or integers. The number 5 is actually all of those things. It is a natural number because you use it to count. It is also a whole number, and it is an integer as well. And then one more of these, example 61.4. On this one, they ask 3 times √2 is a member of what set of numbers? Well, again, it does have to be a real number, so we can write that. But then, we already said the square root of 2 is going to be a decimal that goes on forever. It does not repeat. And even if you multiply it by something, it's still going to be a decimal that goes on forever and does not repeat, which means it can't be written as a fraction, which means it is irrational. And irrational numbers cannot be natural, whole, or integer, so we don't need to worry about those. If it's irrational, that's it. Real and irrational. All right, y'all will be working on problem set 61 here, so good luck on it. If you have questions, let me know, and I'll talk to you later.